In the United States, less than 1/3 of the total land area possesses the soil profile necessary to support a conventional, gravity-fed septic system. When traditional drain fields are installed in these unsuitable, restrictive terrains, the mechanism rapidly breaks down. The soil directly beneath the system becomes hydraulically overloaded, and if there is a high water table, the surrounding earth offers no room for the incoming effluent to disperse. Continuous fluid saturation physically destroys the trench. When the soil remains waterlogged, it is starved of oxygen. This permanent anaerobic environment encourages the growth of a thick bacterial slime layer, which coats the trench walls and completely seals off the surrounding earth. Once that seal forms, the system fails. Passive, gravity-driven treatment is entirely incompatible with heavy, restrictive soils. Processing domestic wastewater in these conditions requires discarding passive drainage in favor of active engineering. Safe disposal in challenging geology means we have to dictate the terms of the environment. We have to actively engineer biological microenvironments to break down the waste and assert precise mechanical control over how that treated water is delivered to the soil. This requires two distinct architectures working in sequence. First, an aerobic treatment unit, or ATU, to handle the biological processing. Second, a low-pressure pipe system to control the final hydraulic distribution. This bar chart details the NSF Standard 40 certification metrics. Raw sewage enters the system, but through active treatment, biochemical oxygen demand drops to 2.4 milligrams per liter, and total suspended solids fall to 1.8. That is a removal efficiency exceeding 99%. By combining accelerated biology with pressurized distribution, we shrink the processing power of a municipal wastewater treatment plant down to a single residential footprint. The life cycle of the aerobic treatment unit begins the moment domestic wastewater flows into the first chamber, the pretreatment tank. This initial section acts as an anaerobic storage unit. Its primary job is to isolate non-biodegradable materials and heavy solids from the main fluid stream, so the rest of the system deals primarily with water. Inside, physical separation takes over. Heavy solids sink to the bottom to form a sludge layer, while lightweight organics, greases, and oils float to the top, creating a surface scum layer. The partially clarified water trapped between those two layers moves forward into the aeration chamber. This is the biological workhorse of the entire operation. Here, a linear blower forces atmospheric air down through a pipe and out through a diffusion stone situated at the very bottom of the tank. This continuous injection of oxygen completely alters the internal environment. It cultivates colonies of highly aggressive aerobic bacteria. Because they are fueled by oxygen, these bacteria operate much faster and break down significantly more organic waste than the anaerobic bacteria in the previous chamber. Converting a stagnant anaerobic holding tank into a highly oxygenated active bioreactor is the specific mechanical shift that allows the system to achieve that 99% organic reduction. Once the aerobic bacteria have consumed the dissolved organics, the highly agitated fluid must be calmed down. It enters the clarifier. Notice the geometry. The solid, sloped walls shield the fluid inside from the aggressive bubbling and turbulence of the aeration chamber. It is designed as a strict quiet zone. Without the constant turbulence, gravity takes over. Any remaining suspended bacterial clusters or sludge slide down the angled walls and drop right back through the bottom opening, returning to the aeration zone for further digestion. What is left rising to the top of the clarifier is a clear, highly treated, and nearly odorless effluent, ready for final distribution. That treated water flows into the pump tank. This is a dedicated holding zone that manages fluid volume using a tiered array of vertical floats. The logic here is strictly mechanical. As water accumulates, it lifts the bottom float, which turns the pump on for a standard dose. If water usage spikes during the day, the rising fluid lifts the middle overright float, which triggers an immediate dose regardless of the timer. If the water hits the top float, meaning the tank is 50% full, it triggers a critical high water alarm, signaling an immediate need for service. The pump tank acts as a mechanical translator. It takes a continuous biological flow and slices it into carefully calculated discrete hydraulic doses. Those discrete doses are what make the low-pressure pipe system, or LPP, viable in sites where gravity drainage is impossible. The LPP relies on an effluent pump pushing water out of the tank through a main manifold into parallel, small-diameter PVC laterals. Unlike conventional systems, these laterals are buried in remarkably narrow trenches, just 12 to 18 inches wide, and kept entirely shallow, no more than 10 inches deep. This keeps the water in the uppermost biologically active soil horizons and avoids the deeper bedrock or clay hardpans. To distribute water evenly, the pump generates pressure head. This forces effluent out of tiny, carefully spaced holes drilled along the laterals. The perforations point upward, spraying the water up into the gravel trench before it slowly filters down into the soil. The entire network is calibrated volumetrically. The pump typically runs just 1 or 2 times a day, releasing a precisely calculated dose equal to 5 to 10 times the internal volume of the pipes. By utilizing pressurized mathematical dosing, the LPP ensures uniform aerial loading. Every square foot of the trench receives the exact same amount of water, completely eliminating the localized overloading that suffocates traditional systems. The LPP is highly effective, but its success relies entirely on the engineered resting periods between those doses. The narrow, shallow trenches are sized so that a single pump cycle deposits only 2 to 3 inches of effluent at a time. Filtering water draws in oxygen, fostering bacteria that convert ammonia to nitrates. The next dose fills the trench, pushing oxygen out. In this anaerobic state, bacteria strip oxygen from the nitrates, releasing harmless nitrogen gas. This alternating cycle completely removes nitrogen. But precision engineering introduces vulnerability. An ATU and LPP combination is a highly sensitive biological reactor. Heavy quantities of bleach or harsh detergents can instantly kill the aerobic bacteria. If the pre-treatment tank isn't managed, suspended solids will bypass the clarifier, flow into the pump tank, and permanently clog those tiny perforations in the lateral lines. Because of these tight tolerances, a strict professional maintenance schedule is mandatory. Components require a structural and electrical inspection every 6 months. The distal ends of the laterals must be flushed annually, and the settleable solids in the pre-treatment tank must be pumped out every 2 to 4 years. When passive drainage fails, human intervention must fill the gap. By enforcing active biological treatment and highly controlled pressure dosing, we can safely and reliably process wastewater in the most restrictive geological environments on Earth.